Hello and welcome to this BBC Microbit V2 webinar. I have with me Jonny Austin, who is the CTO of the Microbit Educational Foundation, and I am the host, Bjorn, and I'm a product marketing engineer at Nordic Semiconductor. So it's just some quick practicalities. The duration of this webinar will be 45 minutes for the webinar and then 15 minutes for the Q&A. Questions are encouraged. Please type them in the top right corner of your screen. You should see ask a question. You should see a little box there. All of the questions are anonymous, and please try to keep them relevant to the topic too. We will have a Q&A towards the end, 15 minutes. The chat, which is below the questions, is not anonymous and should not be used for questions. If you have any more questions after the webinar is done, you can go to Nordic DevZone. So that's devzone.nordicsemi.com for Nordic-related questions. And you can go to support.microbit.org if you need any help with the BBC Microbit. And also a recording of the webinar will be available together with the presentation at webinars.nordicsemi.com. So without further ado, Jonny Austin, you can start your presentation.
Great. Thank you very much. Thanks for having me. So we're going to talk about the BBC Microbit and the BBC Microbit V2. So there's going to be a mixture in this, and I'm going to talk to a kind of mixed audience of, I'm going to assume maybe that you haven't used the BBC Microbit before. So I'm going to talk a little bit about what the device is, a bit about the history of the project, how it came to be, then talk about the V2, and there are going to be some live demos as well. So I'll show you using the Microbit from my computer. And as Bjorn says, please do ask questions as we go along and we'll address them all at the end. So the talk's going to break up into kind of 4 rough sections: some story, narrative, a bit of demos, some kind of under the hood, how it works, and some thinking and some analysis about it. So I'm going to try and signpost these just so you kind of know where we are. So let's start with some story. 1981, the BBC did something called the BBC Micro. So this is a computer that is very popular in the UK, or was very popular in the UK, I should say, and it really changed the UK computing industry. As part of a project with the BBC, who's the national broadcaster in the UK, but also has a remit far beyond just television. They do radio, but they also do news and website, and they do a lot of learning materials as well. So the BBC has this remit much beyond just TV in the UK. And they helped put together this project where a computer went one into every school, and that created a generation of programmers. The gaming industry is very strong in the UK. A lot of that is still credited to not just the BBC Micro, but microcomputers in general and that experience of having them in schools. Fast forward to 2015, and the BBC wanted to do something with a similar level of impact, something that was still about computing and computing education, but really that was right for the 21st century. And they said, rather than giving one device to every school, let's try and give one device to every pupil. And they came up with this idea of the BBC Microbit. And it came in conjunction with a curriculum change in the UK, where the kind of computing curriculum that had been for some years much more about teaching IT, really, rather than computing. So it was spreadsheets, Word, PowerPoint, really useful stuff, but not really anything that would help people program computers. And in 2014, the UK curriculum changed, and the BBC, with its broad remit to teach people the kind of subjects on the curriculum, looked at what existed in the market and determined that it was very hard to teach computing to a broad audience with what was already there. Either things needed a lot of tech understanding or background, they needed a lot of setup in a school, they maybe didn't appeal as much to girls or other groups. And so they set about creating a partnership, a very large partnership, to create the BBC Microbit. And what that partnership created in 2015 is the BBC Microbit device. It's a versatile, programmable IoT device, and it's specifically designed from the very beginning for use in a classroom. So all of the constraints that you have in education were taken into account in the creation of the Microbit. For that reason, it's very, very easy to program. You don't need to install anything on your computer. You don't need any drivers. It is programmed in web browsers, and you download the program onto the Microbit. it has this very simple wireless communication between microbits that allows a really fun experience, but it doesn't need Wi-Fi, it doesn't need pairing. It's got a kind of very education-focused wireless communication. It's battery powered, which means that you can take a microbit, plug it into a battery and turn it into a wearable. You can make a badge, you can connect it to your bag, you can do all sorts of different things with it, no longer tethered to a computer, and it runs the code kind of in the real world. And I think this physical computing aspect of the microbit has been really key in allowing students to understand how the things they do on a computer can actually have an impact in the real world. Part of that is the built-in motion sensors and how instantly interactive the microbit is. Because it has these motion sensors, it can be, it can sense what you're doing, and you can suddenly say, yeah, I can shake it, I can throw it, I can attach it to a door, I can put it on my bike wheel. Someone actually recently attached one to a hamster wheel and just used the fact that it would go upside down once every rotation to measure how far the hamster had run, things like that. And then there's also now an ecosystem of hundreds of sensors and accessories and other things that you can connect up to the board. And the phrase we use for this is that it has a low floor, very easy to get started, but a high ceiling. There's really no reason to migrate away from the microbit. And that's even more true since we launched Microbit V2, which has a much more capable processor. And it's very, very low cost. So it's about £10 if you're buying a large number of them, which means that it's very affordable, not just for individuals to buy, but especially it's affordable for school systems to buy and teachers to buy, like large packs of for many students. And it was designed by a coalition of 29 partners. So Nordic Semiconductor were one of the 29 partners that came together to make the BBC Microbit. And actually, the BBC were looking for various different contributions. I got involved in the project because ARM was another one of the partners that were involved. And Nordic's contribution, as well as engineering, was to donate the NRF 51822 devices for the first drop. So a massive contribution that really helped transform the microbit from what would otherwise perhaps have been a microcontroller device into an IoT device that had this radio communication. So since that original BBC project, where 1 million devices were given away into UK schools for free, the foundation has now been responsible for production of another 4 million devices. And so there are now 5 million BBC microbits around the world being used in education, which we estimate gives us a reach of between 20 and 25,000 students that have used or can use a BBC microbit. So just a little bit of a walkthrough of the hardware. At this point, we often hold up a phone to kind of compare with the device, because I think it's really valuable to understand that one of the reasons I think the microbit works is that it helps kids see at the simplest form what is going on their mobile phone. We've got a display, just like the mobile phone has a display, but it's so simple that you can see each pixel being turned on and off, and you can control each pixel yourself. So yes, it's not like an LCD, but it does help you understand what an LCD in a phone or an OLED, it's probably actually more like an OLED, what an OLED in your phone is actually doing. Likewise, it's got some buttons, so you can see how you program things to react to buttons. It's got some I/O pins. These are actually touch sensitive, and an external power supply. The holes there are for banana plugs, and the pads are for crocodile clips. So really thinking about what's already in the classroom that the microbit can interface with. And this is an edge connector, which we'll talk a bit more about later. So on the back of the board, this is where all the kind of processing happens. So the front is the user interface, and the back is what's making and driving all of that. So it's programmable with micro USB. It's got a reset button and a battery connector. So it's just 2 AAA batteries. And the main processor on the Microbit V1 was the NRF 51822, and on the Microbit V2, it's the NRF 52833. So that's a really big jump up in processing, up to a Cortex-M4 from a Cortex-M0 in the V2, and we'll talk a bit more about that, more flash and RAM as well. So this is where all of the students' code runs, and it's connected to the motion sensors and the display and the radio, which we've got. You can either use Bluetooth Low Energy or a custom 2.4 gigahertz radio protocol that was written by Lancaster University for use in education. And then a magnetometer and an accelerometer as well for sensing motion and being a compass. And actually, really excitingly, there's a set of projects that use the magnetometer, not just to measure magnetism, but to use the magnetism generated by power through a wire, so you can measure whether your kettle is on or not, and actually estimate the power consumption using that magnetometer as well, which is really neat. And then we get on to a really important piece of what the microbit is, this interface processor. which provides drag and drop programming. So this is connected to USB and to the micro or the NRF51 or 52 device. And this is what gives the microbit its kind of extreme ease of use, because it means that when you plug the microbit in, this interface processor, no matter what's running or crashed or broken on this main processor, presents a USB mass storage device interface. So the edge connector is key because it enables a huge range of accessories. I've got one here, so I don't know if you want to switch to my video, but this is an edge connector. The microbit just slots into it like that. This one is a super simple example of an accessory where we've got some RGB LEDs on the back of the accessory and the microbit slots in and out. But that's, if you think about, the dexterity of students, we target kids between 8 and 14 years old. Actually, the dexterity that you need to plug wires into a breadboard, that's really tough. I find that tough. And I'm sort of, relatively well used to using my fingers. So for kids, having that kind of robust interface is really effective. And it's easy to adopt in your hardware. There's no bending of pins. You don't need to do any soldering. We found this has been really effective for people to make accessories for the device. And here's an example of a bunch of the kind of interesting accessories you can get. I used to have them all on one page, but over time it's grown to far more than fits on a page. But from fully fledged robots with wheels to simple speaker boards or traffic lights or environmental monitoring boards, things like that. There's a lot that you can do, extend the microbit with these accessories. So I said that the microbit is a USB drive, and this is one of the key things that helps it work well in the classroom, is that when you plug it in, it shows up as a USB mass storage device on the computer, and that means that you can drop code onto it in order to program it. So I'll do the demo of this later, but you can just drag and drop code onto the microbit drive, and the LED blinks to tell you it's updating, and then your code runs on the microbit. And because of that drag and drop programming, it means that we can provide web-based editors that communicate with, the web-based editors now communicate with the microbit directly as well, but they also don't need to. You can just drag and drop your code on. So these web-based editors are how you write your code. The make code editor here is a kind of block-based that uses Scratch blocks, which is a kind of part of the technology stack that the Scratch team have released open source so other people can use it. So it looks and feels very much like Scratch. And the Python editor, which is a very deliberately a text-based editor designed to have a kind of straightforward, undaunting text-based experience. And again, speaking to the huge success of the partnership model used in Microbit, there are a huge range of third-party editors that target the device. So from Scratch through to the Arduino IDE, there's an editor called EduBlocks, which is actually being developed by a student who was, I think, only 14 when they started working on EduBlocks for Microbit. But that just kind of shows the range of different ways that you can program the device. Mu is a brilliant offline Python experience, which is now built for the Microbit project, but is now in use for lots of other embedded and non-embedded Python platforms. So we really like to foster and support this ecosystem of partners around the Microbit. We see it very much as our role in the foundation to help that. And just an example of the scale then of the ecosystem, there are now more than 200 accessories, 16 third-party editors for the Microbit. We've got 1,000 people on the testers list who are testing things out with us and helping us improve all of the Microbit products and editors. 800 people in our Slack community, about 15 different student projects that have happened at universities around the world. I think it's actually a lot more than that, but we don't know all of the projects that go on. 571 people helping translate the Microbit activities around the world, and 150 approved Microsoft MakeCode extensions. So those are extensions, sort of software libraries for the block-based editor. So that was a very quick kind of tour of what Microbit V1 was and is. And now I'd like to talk a little bit about the changes that come up for Microbit V2. So this is a thing that we announced middle of October last year. It first was available to buy at the end of November, and it's the BBC Microbit V2. So it basically looks exactly like a BBC Microbit V1, and it can do everything that a BBC Microbit V1 can do. And I think it's really important to understand for us, when we first started the foundation, we we went to teachers, and I'd been working in ARM, so I had this idea of kind of an annual technology cycle, and we thought it's 2016, Microbit came out in 2015, we should release a new device in 2017. And we went to some teachers and said, what do you want to see on the new Microbit? And a lot of them just said, oh, don't do a new Microbit, please. We've only just got to grips with the first one. And, I've just done all these resources, please don't change it, whatever you do. And so we realized and kind of started to understand really how important stability was, as well as all those requirements that we took in about being instantly interactive, being easy to program, being able to interact with the physical world. Actually, a really important part of the Microbit is its stability. So when introducing Microbit V2, it was absolutely essential to us that we didn't break compatibility for all of the teachers, educators, resource providers, books out there that talked about this device. So that's why the Microbit V2 does everything the original Microbit does. Can also do some new things. So it can make and sense sound, and that's the most exciting thing that people think about when they think about the new Microbit, is the ability to make and sense sound. It's got a touch-sensitive logo. So that logo there you can touch, and the Microbit can respond to that touch. But I think in the long run, what we'll see as the most exciting change about the new Microbit is that it uses a much more powerful processor, and that allows us to do some real AI and kind of machine learning experiments with the device and help kids understand that. So just to give you a quick rundown of the kind of where those things sit, that's the touch sensitive logo. We've got a microphone activity indicator. I'll talk a bit more about that later, but we think it's really important to be very explicit about when the device is and isn't recording or listening, as it were. And then the notched edge connector makes it much easier to put crocodile clips onto the Microbit edge connector. Just one of the observations was if you've got very small hands, it's hard to open a crocodile clip wide enough to clip it on here. So this makes a difference as well. It's a small thing, but it's helped people with the new device. We've got a power indicator because the Microbit V2 is actually capable of going into a much wider range of power and sleep states, including a very low power sleep state. That means you can run projects for months at a time, doing data logging and waking up from sleep to log data. And this power indicator helps people understand whether the device is on, awake, or asleep. I'll demo that as we go through the live demo. Microphone on the back and the speaker. So a nice example that we did to kind of demonstrate what the Microbit V2 was capable of early on is a little machine learning demo. So this Microbit now is listening to what I'm saying. And I don't know, everyone, if you want to switch to the view of the Microbit, if you haven't already. This is listening to what I'm saying and listening for me to say the word Microbit. Not that time, Microbit. Hooray. So it's a pretty quickly built model. It's not really there yet, but it can distinguish a bunch of other things from Microbit. It seems to have gone a bit haywire now. It's a bit overfitted. It works a lot better if I'm facing it. I'm not sure if you can see this. Microbit. No, we can talk about how we improve this model later, but it did lead to one of the more fun team meetings we've ever had, where everyone in the Microbit team said the word Microbit 3 times in order to get this training data. And then we worked with a company called Edge Impulse, who I think will be familiar to a lot of you, especially if you've worked with Nordic recently, or Nordic Technology recently. Edge Impulse are doing really interesting machine learning on the edge stuff, and an incredible platform for taking the data, cleaning it, collecting it, and building those models in C and C++. So they did an amazing job of turning this demo around. And yeah, that's interesting. And then using the same platform, using the Edge Impulse platform, the team at OKDo built a dance machine learning move detector, which was super cool for actually engaging students who love to dance and detecting what kind of motions they're doing. You can find both those projects online. Okay, so that's about time, I think, for me to kind of put my money where my mouth is about this being easy and do a bit of a live demo. So I'm going to switch over to Chrome and to a MakeCode window. If you want to just give me a shout that you can see the MakeCode window.
Yes, I can see it.
Great. So this is a very small, in terms of code, example of what you can do with the Microbit. And so when we start, we set the radio group. And this is because the radio protocol for the Microbit allows multiple groups, and each group doesn't receive messages from the other group, or so a group will only receive messages that go to that group. So it's good if you're doing work in a classroom. You might want to put, have 5 or so different groups that are all playing games on the same radio channel. It's not actually the same as channel. There's also a channel command, but this group is an application layer construct. So then the microbit, I said, can detect motion. So when we shake the microbit, we're going to, when the microbit detects a shake, we're going to send a string on the radio. We're going to send duck. Actually, if you look at our code, it doesn't really matter what we send because we're not checking what string is received. But we're going to send the string duck, and then we're going to clear the screen. And then when we receive something on the radio that is a string, then we're just going to show a duck icon, and that's it. That's all this program is, and we're going to put this on 2 microbits. So I talked about the fact, well, maybe I didn't. There's a simulator here, so this is doing nothing. But if I shake my mouse, what that does is the first time I shook it, it sent a new radio message, and the simulator detected that I'd sent a radio message and created a second microbit so I could test my program. So now if I shake this one, it's teleported a duck over to the first microbit. If I shake this one, teleport my duck back over. If I shake this, the duck teleports back. And it's a very simple demo, but once I get it onto the real microbits, I think you'll see that it feels really compelling for kids. So what I'm going to do to demonstrate how the drag and drop programming works is I'm going to click download here in Chrome. And that is going to create a file to run on the microbit, a hex file. And if I show that in Finder, it'll be in my downloads directory. So if I now plug in a microbit, actually, you know what I'm going to do? I'm going to switch cameras so that you can see what's going on my desk. Hopefully you can see my collection of microbits now. So right, there are my microbits. I'm going to plug it in. And I'm going to drag and drop the code from the downloads window onto the microbit drive. And then the LED on the microbit starts to flash. Blinkety, blinkety, blink. I was joking this morning that I'm worried we might be teaching people that the reason it's called flashing is because the LED blinks rather than writing to the flash. So we've got to be careful about kind of language we use. And so now this microbit has that program on, and I'm going to do the same for another microbit here. I'm going to use the green one. So if I also do that, I'm going to put plug the first microbit in. That's now running on battery. Second microbit's running a different program. This is actually running a program that's listening to my voice and drawing a little mouth, which is also fun. You can look again at that program later. But if I drag and drop the same duck program onto this microbit now. So this is a microbit V2. So the first one I put the board on, this is actually a V2 RC1, but that's fine. The first microbit that I put it on is a microbit V1. The second one is a microbit V2. And despite these being different versions of the microbit, they can still send radio messages between each other. They're both Nordic radios. They work perfectly together. So this is a 51822 talking to a 52823. And this is, super simple, but really fun. And it often for kids doing a demo like this is the first moment where they get that excitement and realize, wow, my programming doesn't just have to be on the screen. I can take this away. I can send messages to my friends. You can actually detect how close a radio well, you can detect the signal strength. It's not the same as how close. You can also see the other subtle change we made on V2 was to use a matte silk screen, which certainly makes a difference on video in the evenings at least. So that's just a simple demo of how the MakeCode editor and the kind of radio features can make very, very fun, easy projects for kids. And also how a single hex file here, the microbit duck.hex, I dropped it onto the microbit V1 and to the microbit V2, and the same program just worked flawlessly on both, which we'll cover a bit later as well. Switch back to me video, just in case I end up holding something up to my camera. And I will go back to my slides. Great. So that was demo 1. So what's actually going on here? How, at a technical level, what are we looking at? So this is the block diagram of the microbit V1, and it helps to kind of anchor ourselves in the more simple design. We've got an NRF 51822 as the main processor, a an NXP or Freescale KL26Z as the USB processor. They were part of the original project as well and donated silicon. That's part of the reason we ended up with this architecture. We've got a motion sensor, and it's an LSM303 AGR connected to an I2C bus, an LED matrix, buttons, and the edge connector. And we've got UART and SWD running between the two microprocessors. So this processor is capable of programming the NRF51822, and the UART is passed through over USB. So the microbit V2 predictably has quite a similar block diagram. The newer chip. So the 52833 has 512K of flash compared to the 256K of the V1 or the NRF51822, and 128K of RAM compared to the 16K of RAM on the microbit V1, the NRF51822. So that's a huge upgrade in terms of memory, and that's already made a difference in the kind of things we can do. Although one very capable student did manage to make a handwriting recognizer with an SPI optical mouse camera on a microbit V1 by seriously compressing the neural network. It's extremely hard work to do it on microbit V1. So doing that kind of stuff on microbit V2 where you can run TensorFlow light micro is a lot easier. The other thing we've done is we've made the KL27, the interface processor, an I2C secondary device, so that these two devices, the NRF52833 and the KL, can cooperate for things like power management and LED states. And it's actually possible for the NRF52 to request that this other microprocessor puts the LEDs off, for example, if you want to save power or other kind of power saving states. I think that's probably all to say. Well, obviously, the mic and the speaker are added onto the Nordic side of the processor, the Nordic side of the diagram, and we have a slightly more normal LED matrix layout on the microbit V2. We had a strange kind of interlaced one on V1. So I talked a bit about that I2C communication that we've enabled. So the things we do over that are device information, what version of the board are we, some power management, setting the LED states, and we've also enabled at alpha level at the moment an I2C flash storage interface. So this I2C secondary device can allow over I2C, the Nordic can write to the flash here, and that actually flash can then be exposed on the USB drive as a file. So for kind of data collection in schools activities, we're just doing some pilots around that now as an alpha to see how effective that is. And we've even got the possibility, also not yet fully implemented, but we've got the possibility of doing power measurement, which means we can get fairly crude measurements about how much power is being consumed by the whole device, whether it's sleeping well or whether it's whether maybe you're in a really tight loop versus having some event-based programming. There's something to expose there, but that's nothing in terms of the capability that you'd expect on a professional dev board. It's much more of an indication of which broad range you're in from a power consumption point of view. Right, so I mentioned we have these universal hex files, and we also talk about universal editors. So that single hex file that I dropped onto both versions of the board is a really important part of our continuity story, and we worked very hard to make sure that this would work smoothly. So in MakeCode here, I can use blocks from all of the original categories, but you see I've got a category here, microbit V2. So these blocks will only work on a microbit V2 device. And the nice thing about these is that if I use, for example, the logo is pressed test or the sound level blocks, if I create now a new input block, so when I push button A, then I'm going to show on the screen the sound level. So the nice thing about this is that this program, even though this sound level block can't work on a microbit V1, this program will work on a microbit V1 until the user presses button A, at which point it's going to throw an error on a microbit V1. So if I push button A now, you'll see the simulator converts my microbit into a microbit V2 because it knows it's a V2 device now. And I've got simulated sound level, and I can simulate this. But if I were to put if I were to, instead of using the sound level block, take, for example, the on logo pressed block here or on loud sound block, if I put this program now, I probably have to put something in here. So logo pressed, we'll just show a tick. If I were to now put this on a microbit v1, then the program would throw an error immediately, because this event handler is never going to fire on a v1, so we can't have that working smoothly. So we try and fail as clear in the clearest way we possibly can, and we try and make code work as well as it can until it can't anymore. And in MicroPython, then the v2 features are available via specific APIs that throw runtime errors on v1 hardware. So just a bit of a graphical demonstration of what's going on here. We've got a combined hex, a universal hex file that contains code for both the microbit v1 and the microbit v2 sort of whammed together. And if you put it on, if you're using features that work on both boards and put it onto any one of the 3 different versions of microbit that exist. So microbit v1.5 code actually runs on a v1.5 and a v1.3. Then it will run on all versions of the board. But if instead we use some v2 only code, then we get an error on the v1s, but from the same hex file. So we still have a hex file that works properly on both. And if we didn't do this, if we just had only the plain v2 hex, for example, and we only distributed that, then if you put that on an existing microbit v1, it looks enough like a valid Cortex-M hex file to actually program on the device and then immediately crash. And so it's not clear at all to kids what's going on. So part of this was about making the errors really explicit. For us, it doesn't, it's not ideal that this doesn't work, but the key thing was that the error was really explicit to a user what's going on, so that they get some feedback rather than just seeing a blank screen. So that's the universal hex side of things. And then we've got on the, I talked a bit about that microphone indicator. We were really careful when we were doing the microbit v2 design to recognize all of the things that people loved about the existing microbit and the huge amount of collaborative design work that had gone in. We didn't want to change the look and feel of the microbit, but we did think it was really important to enable teachers to have conversations with their students about privacy, about what it meant to have a device that could listen, record audio. So we went for this microphone indicator, which is actually a side mount LED mounted on the back of the board and a hole in the copper and then some solder mask on top that allows us to get this glowing microphone effect through the board, but without having to kind of add anything extra on the front face. And when the LED is not on, you basically can't see that microphone indicator until the microphone comes on. And here are a few kind of desk-based prototypes and experiments for what this might look like. This was an idea that maybe it should be like a recording light. This was us working just with an old prototype microbit v1 to see whether we could get the light coming through, and then we did some test boards as well. So there's lots of detail that goes into the kind of user experience of this microbit. Lots of work that goes into making sure it is just right for the classroom. So I want to talk now just a little bit about the influences in microbit v2, the kind of the things that were our, I guess, some key motivators. And one of them, as I've already talked about, was microbit v1, which was a brilliant piece of collaborative design done by these 29 partners, the visual design predominantly by a company called Technology Will Save Us, who do awesome stuff with tech for kids. So that's a really nice piece of design, and we wanted to hold on to that. But early in the microbit v1 prototyping process, the logo was gold. And those of us that were involved in that sort of thought, oh, wouldn't it be so cool if we could touch this? But it was never really possible on the v1. So we wanted to bring that feature to the v2. So it's a bit of a throwback to the original project. We also pulled in all of the things that we'd seen people doing with microbit, the cool features, the cool things people had added, the cool accessories, and tried to look at what people were enjoying doing with the microbit around the world and how we could make that stuff easier. The other thing, I'm sure you've noticed that the microbit looks like a face with 2 eyes, and you can do lots of different kind of face-related things on the microbit. And that was all about making sure the device was kind of easy to have a connection with. It needed to feel like something friendly, something approachable. And these 2 little knitted characters are actually things from a children's TV program in the UK called The Clangers. And they can't speak, they can only make sort of whistling sounds. And they're very cute, and kids really love them. And we wanted the microbit, when we knew we were putting a speaker on the microbit, we didn't want to have something that just went, meh, like have these ugly buzzers and beeps. And we wanted to bring the kind of same aesthetic design to the sound of the microbit as we brought to the visual design of the microbit. And so the clangers were one of our inspirations, these friendly characters that can only communicate in squeaks and whistles. Similarly, with the microphone and the sound, I have, I don't know, Bjorn, if you want to switch to my camera, I have this really horrible parrot, which is actually amazing.
Really horrible parrot, which is actually amazing.
That listens just in the background to what you're saying and then parrots it back.
Listens just in the background to what you're saying and then parrots it back.
And it's horrible and hilarious, and it kind of moves. It's got this was one of the things we said. We want kids to be able to make something as annoying and excellent as my parrot. So the parrot was also a key influence for us. And then we looked at actually what can you afford on the microbit. Being low cost is very important. So we looked at the frequency response of a whole range of different low cost speakers, and realized that they all have this frequency response that's really good between 2.5 and 5 kilohertz. And that's also very well aligned with birdsong. So another thing that was, guided me at least, was trying to think about how can the microbit be friendly like a bird? Can we make good birdsong? And this is something we haven't yet realized in the wider, what's been exposed to kids, but I would love to see some kind of birdsong generation going on the microbit, seeing the microbit singing automatically generated songs, or maybe songs based on the user interaction, and maybe even whether we can recognize birdsong using the microphone and some machine learning algorithms. So I think another of the influence was birds and that kind of natural effect rather than the buzzy effect. And the last shout out goes to conference phones, because microbit v2 was developed basically remotely. We never went out to China in the whole development process, and worked very, very closely with the team at Farnell, or Invest in Farnell, and had to do lots of posting of boards around. But really, this is here because we thought the microphone LED on these Polycom units is a nice example of the sort of clear interface we liked. And lastly, smart speakers. I said at the beginning that behind microbit v1 was this idea that we wanted to explain to kids or show and demonstrate what a mobile phone was and what it did. And in the time since the original microbit was done, we've seen the rise of smart speakers that can respond to your voice and can do intelligent things. They've got machine learning going on. And so we wanted the microbit v2 to be able to present and provide that same kind of understanding at a simple level of what was going on inside your smart speaker, in the same way microbit v1 lets you see what's going on inside your phone. Right, so time for another bit of demonstration. I think I'm going to do a little bit of sound stuff. So just to give you an idea, I'm going to play some of the sounds. So I'll switch back. Actually, I think we'll just use my camera for this, because I've already programmed this in just to have a listen to some of these sounds. So
just a quick comment, Johnny.
Yeah.
We don't have too many questions in, so if you want to talk for another 10 minutes, that's fine, and then we'll do a 10-minute Q&A.
Great,
Yep.
We'll do that. So here's my microbit. It's showing a little picture of a giraffe at the moment. If I push button A, or in fact, if I reset it, it's going to make a little hello sound. So that's our little friendly hello. If I push button A, it's going to make a happy sound. And if we worked with a sound designer to kind of build these sounds and get them feeling really friendly. And this is our sad sound for a sad microbit. Oh, sorry, microbit. And one of our design goals was trying to, really trying to make sure that when the microbit made a sad sound, you did feel sad, and I feel sad when I hear that sound. So we were going for that kind of feeling, and I think we can look at how easy it is to build this kind of program. Back on my screen, if we just create a new program. You can do, so we're going to go on start, music, play sound, and we've got we'll do a hello. And I was using buttons before, but if we do, we can use the buttons. On button A, duplicate this block and play a different sound. I'm going to just mute the simulator because it's going to keep playing noise at me now until we finish. So we'll go happy, duplicate this again, and on button B, we will go sad, and then we can also put in the icons to show on the screen. So do a heart for happy this time, and we will do for sad. We'll do just an empty face. That's even more sad. Not got the energy to be sad. Maybe they've been in lockdown too long. And then on start, we'll just show another picture. What will we show? We will show a small heart. So that, that's a super simple program, but we can also do, we've got this on loud block. So let's do on loud. When we hear a loud sound, we can do something like, we will play, what do we want to play? We'll do twinkle when you hear a loud sound. So before I showed you drag and dropping, the other thing I'd like to show is that you can actually, I've plugged in a microbit here that I've used before with something called Web USB. So if I unplug this, you'll see this download button changes from being a disk download to being a USB button. So when I plug my microbit back in, it will detect that it's a USB device that I've paired before, and it says it's connected to the microbit. If I hit download now, this is just going to actually program the file directly to the microbit. So instead of doing it that way, what I'm going to do is I am going to pick one of the ones that I haven't already paired, so that you can see the pairing process. I think that's useful to show, given that Bjorn just gave me a tiny little bit of extra time. So, oh, I've used that one before as well. That's a shame. Well, okay, so if I disconnect, we'll unpair this one. Got a bunch of them. Unpair them all. There we go. Reload the page. So now we can go through the pairing process again. And this is a Chrome feature. It's a fantastic Chrome feature because it really simplifies the experience. If I do pair device now, pair device, I can select BBC microbit, click connect. And now the first download can sometimes take a long time. After that, updates are almost instantaneous because we only have to reprogram the bit of the flash that actually changed. So that wasn't even very slow. So that was our twinkle sound. If I clap my hands, oh, there we go. There we go. So that's responding to sound, and you can see the microphone LED has come on to tell us that we are. I don't know whether you're looking at the microbit itself. And then to shut it up, because that is really important. If I push and hold the power button, if we go to the camera view, the LED fades out. And then when I let go, this is now in standby mode. So because it's on USB, we still want it to be available over USB for flashing, but we've basically turned it off, which is really great as a mute feature. If I push that button, it's going to come back on and start making all of its noises. I can then turn it off again. If we're on battery, that LED goes completely off and the device is in very low power sleep. Right, I think at that point, we should head back to the slides. So this is a little bit about the Microbit Educational Foundation. I think it's important to have a sense of who we are and what we do, because we're a not-for-profit, and well, I'll talk more about that in a moment. So back to the story. In 2015, the BBC, we said we'd done the Microbit, but in 2016, the BBC said, look, we'd like the Microbit to continue and have a life of its own, but it's not with us. It's not inside the BBC. That's not their speciality. So they said, we want to make a not-for-profit foundation, and we want to bring together a partnership of organizations to found it. So these are all the founding partners. We're really grateful to them. And they helped create the Microbit Foundation so that we could then take on the kind of what Microbit was at the time, keep it going, extend it. And now with Microbit V2, I think we're giving it a new future as well. So the mission of the foundation is to inspire, or the vision, sorry, is to inspire every child to create their best digital future. And I want to break down what this means a little bit, because we spent a long time trying to put this phrase together. It's a simple sentence, but it's really key. So inspiring is there because we don't just want Microbit to be a learning tool like a ruler or a calculator. We want it to be something fun, something that kids really engage with and really enjoy. This every child component is absolutely essential, because for us, the Microbit is not just about having kids that already know they're interested in computer science create their best digital future. It's about significantly broadening the diversity in the kind of computing ecosystem. It's about attracting people who didn't already know computing was for them. And in the UK, at least, and lots of Western countries, there's a big difference in the number of women that take computer science at A level and go into it as a career compared to the number of men. So we have a particular focus on making sure that girls are engaged with computing, as well as other underrepresented groups. So then this create their best digital future is our statement to say, we don't know what the right thing is for the future is. We don't know how technology should be applied, but we want a diverse group of people to be creative about how technology should be applied to create the future they want, rather than the future that a small, narrow group of people think is right for the world. And I think that's, to me, one of the most important things about the foundation, is that we're helping to inspire the next generation to use technology in a creative, beneficial, and diverse way. And this is the mission. This is kind of how we do this. So it's actually best, I think, to let you read this. But for me, one of the key things for everyone, the whole of the foundation, is to inspire all children to participate in the digital world, particular focus on girls and disadvantaged groups. But then the tech team, I feel as responsible for the tech team, that we make Microbit the easiest and most effective learning tool for digital skills and creativity, is absolutely core to what I do in the foundation, and the work I do with partners like Microsoft and the Python Software Foundation in building these editors that make it really easy to engage with and program the Microbit. As far as education resources go, we work very closely in collaboration with people all around the world to make sure that we don't treat Microbit as a one-size-fits-all solution. We don't just kind of roll out exactly the same thing to everywhere. We work with local partners to tailor things to the local curriculum, tailor things to the way the computing needs to be taught in those environments. And we like to support communities of educators. We like this to be a partnership and an ecosystem. So one of the ways we do that is by providing excellent resources on microbit.org. So one of the tabs I've got open here is microbit.org. And this is the homepage. If we take either projects or lessons, then we can see some of the things that you can do with the device. So I'm going to start with Do Your Bit. This is a challenge that we run every year with our partners to encourage children to think about the ways, or think about these global goals, and think about the ways that technology, and the Microbit specifically, almost as a conceit for technology, can help students, or can help us address these global goals. So the two we're focusing on this year are health and well-being and climate action. But I think it's really great to have a program that focuses on doing social good with tech. It's not, that's one of the many strands to what you can do with the Microbit. So then in Make It Code It, we also have a whole bunch of straightforward activities that get you started with the device that are all broken out. So if we take the animated animals one, this is just a simple program to show you, and we can render the code for you in the website, make code and Python to show you what to do. So here's an example of an animated animal. And that's just going to be a duck that moves up and down. So we also have much more structured lessons for teachers to use, units of work that are kind of planned out and give you a kind of whole breakdown if you want to teach a number of different things with the Microbit. And these ones here have Microbit activities associated with them. So this is a growing corpus of very education-focused materials that you can use with the Microbit. Right. And the lessons are kind of linked by age group. So we aim to provide different things for the different key age groups that we work with. And I think for me, one of the things that really got me excited by the Microbit as I was working in ARM was that education with the Microbit is about students inventing things and expressing themselves, and the technology as a tool. This is about the kids doing stuff that matters to them and learning to code, learning to use technology, because it allows them to achieve the things they care about. And that makes such a difference in terms of motivation and in terms of engaging that diversity of people, is the way we kind of flip that aspect. Okay, so the last thing I want to talk about before we do questions is a little bit more on the kind of detailed tech of how the Microbit works. So tech.microbit.org is somewhere between a wiki and a data sheet for the Microbit. It has loads of information about the way the device works and how you can interact with it. Schematics, details on the edge connector. There's a reference design there for the Microbit, which is a fully open source reference design. And for example, probably don't want the hex creator, but if you want to create a universal hex, you can do it there, or you can learn about the hex format. For example, I was talking about that universal hex format. We've documented what that is and how it works here if you want to start creating universal hex files. So if you're working on another project that you think would benefit from this, you can use that information. So that's tech.microbit.org. I encourage you to have a look over it. I'm going to talk just about a few more key features of the tech stack on the Microbit. So the device abstraction layer is built by Lancaster University, who were one of the founders of the Microbit Foundation and key in the Microbit project throughout. And they've built this embedded, it's sort of RTOS, sort of runtime, very lightweight operating system, which has an event bus for synchronization. But all of the official editors build on top of this CODAL environment, which builds itself on top of the NRF SDK and soft device when we're doing Bluetooth stuff. So this enabling kind of system means that the editors, even if you're using MicroPython or MakeCode, they've got the same kind of semantic feel, the same core features, the sounds that I played to you sound the same. All of that stuff is kind of implemented in the C++ layer. And we've already talked a bit about the interface chip and how that allows the online editors to communicate over USB. But because we have that device abstraction layer and much of the functionality is implemented in C and C++, it allows us to do these web-based editors where we don't have to do any compilation in the cloud or any kind of live compilation for the students. What we do is we pre-build a blob, which represents the kind of vast majority of all the things the microbit can do. And then we combine that with a script that, or something which represents what the user told the microbit to do. So in the case of MicroPython, that's fairly straightforward because the MicroPython is an interpreter. So we've got an interpreter, and then rather than just sticking the file in there, we actually build in the browser a little file system blob that contains the student's code as main.py, and that gets run. So that's kind of neat. And then MakeCode took a similar approach, but they, instead of building an interpreter, they have a sort of like a jump table. So they build all of the C++ and the CODAL, and then they compile the student script directly into ARM assembler in the browser, and that ARM assembler calls into the runtime. So in the same way, you're just compiling the student script from JavaScript into Thumb2, and that means you kind of do this offline once every time there's a new release of the runtime, and you build the kind of shell hex file, and then in the browser you take the student script, you compile it first into JavaScript, and then that gets combined into ARM assembler, concatenated with the original shell hex file and put onto the microbit. And so you do this once, and then this happens in the user's browser millions of times for every kind of release. And that really helps us scale, means we don't have a lot of kind of server costs. We don't have to manage compilers. And crucially, we don't have to send the student scripts anywhere. We don't have to send the scripts to a server. And so we don't need to worry about holding data of children 13 and things like that, which is a real win. And then you've already seen simulation, but I think simulation makes a big difference to the microbit experience, being able to try your code out in the browser before you have to run it. Right, the last thing I want to say is that, you know, as far as Microbit V2 goes, we're really right at the beginning. We've just released this new hardware. It's got a lot of exciting capabilities, and we have not taken it even out the gate yet in terms of what we are enabling. And so, you know, we see, because of these stability requirements I talked about and how important it is to keep the hardware and the software stable for teachers, we expect, you know, Microbit V2 to last for a very long time, and we want to be continuing to add features, experiences, cool things that people can do with the microbit. And this is an invitation really for anyone interested to come and get involved, either use the official editors, build something around it, but demonstrate what the microbit's capable of. Go and do something awesome with it, show it to the world. And then, you know, over time we're kind of good at bringing that stuff in and making it available in an education context so that it can really work for kids.